topic is optimization. And well, we will see this topic includes a lot of word problems. We will have an objective function and a constraint equation. But before I get into that, I want to remind us what we have done with optimization so far. So in Brown, let's recall, if you have a continuous function on a closed interval, then this function attains both a global max and a global min on that closed interval. And this is something we discussed much earlier in the semester. So to illustrate with an example, I just chose one that came off an old final exam. So what we want to do here, we have this function on a closed interval. We will find the global extrema. What do we do here? Well, the first thing that we need is to find critical points, and this involves calculating the first derivative. Here, this is a chain rule. The derivative is like this: e to the x cubed minus 3x times derivative of the inside function, which is 3x squared minus 3. Then the critical points are the x values where this derivative does not exist or is 0. Okay, well, if we look at this formula, it's fine in terms of a formula being defined, but we know the derivative, because we're looking on a closed interval, it does not exist on the endpoints. So I do have critical points at the endpoints, 2 and minus 2, but also I need to set the derivative to 0 to find the other critical points. And maybe let me just factor while I'm at it. Okay, this 3x squared minus 3 factors into 3 times x minus 1 times x plus 1. And now if we set this to 0, this first part is e to something, never 0. This is just a number, 3. Of course, that's never 0. And so we set this to 0, or we set this one to 0, and we get, x plus 1. We get 2 more critical points. Here we have a critical point, x is 1. And here we have a critical point, x is minus 1. Okay, so we have 4 critical points for this function on this closed interval. And then to find the global max, global min, we do not need a first derivative test here. What we need is just the highest y value, global max, and the lowest y value, global min. Okay, so what I typically do is make a chart, x. This is the original function. And I list my critical points, 1 minus 1, 2 minus 2, and then y value. Well, here is the function, so I'll make a box down here to compute. 1 cubed minus 3 times 1 is negative 2. So here is e to the minus 2. Minus 1 cubed minus 3 times minus 1. This is 3 minus 1 is positive 2. This is e squared. And then we want 2 cubed minus 3 times 2. This is 8 minus 6 is 2. Over here, I'm just computing what's up inside the exponent. So the function value here is e squared, and then we have minus 2 cubed minus 3 times minus 2. This is minus 8 plus 6. We get negative 2. So this one's e to the minus 2. Now we see the function value at all 4 of these. And in this problem, the highest is here and here. E squared is certainly bigger than e to the minus 2. So we have an absolute max or global max of y equals e squared, and it occurs at two different values, -1 and 2. Okay, then we have an absolute min. Well, the lowest y value is here and here. We have an absolute min of e to the -2. Or global min, y equals e to the -2, and this occurs at 1 and -2, okay? So this was just a refresher to remind us about global max and global min on a closed interval. The extreme value theorem that guarantees you have a global max and global min for a continuous function on a closed interval is what our text calls type 1, talking about optimization. Now, many applications, the word problems we will see today, we're not working on a closed interval. And so another possibility, which I have written as type 2, is we want to maximize or minimize a continuous function on an open interval. And this is more challenging. For example, a global max, global min doesn't necessarily have to exist on an open interval. But there are some things that we can say. So let's suppose f of x has one critical point on this open interval, which means that the function is either differentiable on the entire open interval and the derivative is 0 at, let's see, I'll call it something, x equals c, or the function is differentiable everywhere except for x equals c, where f prime of c does not exist. So maybe before I say anything, I'll put that in parentheses. We can add that, except potentially not at the critical point. In any case, here we go. We have only one critical point, and that's the important part of this. Then we may use the first derivative test for global extrema. We know the first derivative test is something we use for local max, local min, but when you are in the case where you have one critical point, the first derivative test will tell you not only is it a local min or local max, whichever it may be, but also that it is global. And the idea is quite simple. We have an open interval, a to b. We have only one critical point, and then say the function is increasing and then decreasing, okay? It's a global max as well as local max. Or similarly, if the function is, so here's c, if the function is decreasing and then increasing, and this is our only critical point is at c, and here's the interval a to b, well, you see, it's a local min by the first derivative test, but because it's the only critical point, first derivative test will tell you it is a global min. And so this is very nice. When we are in the case of one critical point, we may use the first derivative test to conclude that we have a global or absolute max or min. Now let's discuss the terminology of optimization and the types of problems we will see in this section. First of all, we have an objective function. And the objective function expresses a quantity that is going to be maximized or minimized. And quite often, typically the objective function has more than one variable in it. Okay. Then we also have what is called a constraint equation. This is an equation. So it's an equation. It's something equals a number, okay? And it relates the variables to each other and any constraints in the problem. So what maximization or the optimization problems of this section, we want to say maximize or minimize some function subject to a constraint equation. Here's our first example, and quite often I think the hardest part is step 1, which is translating a few sentences into a constraint equation and an objective function. So let's work on this here. What does the first sentence say? The sum of two positive numbers is 16. Well, if the positive numbers are x and y, this would say x plus y is 16. Now, this is an equation, and it is the constraint equation. Now, what are we trying to maximize or minimize? This is the second sentence. And we read smallest. This is a minimization problem. What is the smallest possible value for the sum of their squares? Well, the sum of the squares is this. Maybe I will just call this capital S. Okay? This is our objective function. And we want to minimize. Okay? Well, what we need to do, because we know how to maximize or minimize a function of one variable, okay, well, we just talked about that some. So we need to write this objective function as a function of just one variable. This is where the constraint comes into the picture, because I can use the constraint here and solve. I get y is 16 minus x. And so my objective function now, as a function of x, we want to minimize, I'll call it s of x, which is, it's x squared plus 16 minus x, quantity, squared. This is x squared plus y squared. Now what is the domain? Well, both numbers are positive, which says that x needs to be positive. And then because y must be positive, that means x must be less than 16. So we will minimize this function on an open interval. Okay, great. We begin, look for critical points. This involves the derivative. So s prime of x equals, well, we have 2x, and then technically this is a chain rule part. We have 2 to the 1, and then times like this, derivative of the inside function, okay? Now this, we can simplify this sum. Maybe I will simplify this as I set it equal to 0, because these are the critical points where the derivative is 0. I have a 2x, and then I have a positive x times 2. I have 2x and another 2x. Altogether, I have 4x. And then, if I multiply 16 by 2 and by minus 1, I get minus 32. So this part here is the derivative, and I have set it equal to 0. We get x equals 8. This is the only critical point. And it's in my open interval. Very nice. Now, well, we need to make sure, you see, I'm looking for a minimum here, so make sure it corresponds to a minimum. And just like I just discussed, we have one critical point, so we can use the first derivative test. Here's 8. If I needed the intervals For instance, when we did intervals of increasing and decreasing, this would be 0 to 8 and 8 to 16, okay? And then I pick a point in each interval. I can pick 1, I can pick, say, 10, and then test the derivative. Well, the derivative is quite simple here. It's just a linear function, but s prime of 1 is 4 minus 32, definitely negative. S prime of 10 is 40 minus 32, positive. So this goes minus plus. Okay? Let me move over here. Now, let me just sketch what's happening. Here's 8. My function, s, goes like this. It is decreasing, increasing. So we see here, we in fact do have a minimum at x equals 8. Okay, now we're not quite finished. The final thing to do is to read, usually the last sentence, and see what it's asking for. We want the smallest possible value for the sum of the squares. This is asking us for a function value. This is asking us not for x equals 8 as the answer. It's asking us for the s of 8. This, the sum, okay? So the answer here is s of 8, which is, if we look at the function here, s of x, 8 squared plus 8 squared, which is 64 plus 64 is 128. And this is our final answer. It is the smallest possible value for the sum of the squares. Now for the next example. And this one, just like the next few we will do, it's really important that you draw a picture. Quite often with the objective function and constraint equation type problems, you want to begin by drawing a picture. So let's read the problem. Of all boxes with a square base and volume 100 meters cubed, what are the dimensions that minimize surface area? First of all, like I said, let us draw a picture. We have a square base and then we have a box. This will help us set up all the equations correctly. Here, my base, I will label this x. Well, and this is also x. Here's my square base. And then my height y potentially is different. Now, what are we told? The volume is 100. And so we have the volume is x times y. X squared y is 100. You'll notice this is an equation, and this is my constraint equation. And then we want to minimize surface area. This is when the picture really helps. So the surface area, maybe I will write this as S again. What is this? Well, you notice I have 6 sides. I have a bottom, a top, and I have 4 around the sides. And the bottom and the top are both x by x. So I get 2x squared. And then each of the 4 sides is x by y. So I get 4xy. This is my objective function. And as it's written right now, we have 2 variables, but we will write this in terms of 1 variable, just like we did in the first example, using the constraint equation. We want to minimize. Okay. Here we go. I use this, let's see, I'll just solve for y in terms of x. That way I don't have to take a square root if I try to solve x in terms of y. So here I have y in terms of x, and now I can write, let's see, maybe I will do it up here. I'll go like this. S of x, we have 2x squared plus, well, it's 4x times 100 over x squared, which will be 400 divided by x. This is my surface area as a function of x. Now, what interval am I looking at? Well, x must be positive and y must be positive. But you see, no matter how big x can be, I can still have a y such that x squared y is 100. If x is like 10 million, y would just be 100 divided by 10 million squared, which is very, very small, but it still is possible to make a box that way. So my domain here is 0 to infinity. Okay, great. And we want to, I have it here, minimize. So here is the function I'll work with. Now let's take the derivative. 4x minus 400x to the minus 2. We want to set this equal to 0, and I will write it this way. So let's move 400 over x squared to this side. We get this equals 4x. And now you see, if I just multiply both sides by x squared, I get x cubed is 100. Okay? So this says x equals the cube root of 100. And this is my only critical point. So we are in this beautiful situation where we have one critical point. And so we can use the first derivative test to figure out if this critical point corresponds to, well, it's a global max or global min. And hopefully, because I'm trying to minimize, I will get a global min here. I kept what I still need on the board. I kept my original function, s of x. I kept this relationship between y and x, then the derivative, and this one critical point we just found. And then I erased the rest of the work so I have space to continue. Well, let's use the first derivative test. Here is the cube root of 100, and then my intervals would be 0 to the cube root of 100 and cube root of 100 to infinity. And then we want to test the first derivative, which is still on the board. So let's pick a point. Maybe here we can pick 1. And here, 100. Okay, that's definitely bigger than the cube root of 100. And we will test the derivative at those places. Here's the derivative. At 1, what do we get? We get 4 minus 400. Oh, maybe I'll write that. Definitely negative. And at 100, we get 400 minus, oh, well, this is a number less than 1. It's 100 squared. Okay, this is definitely positive. So what we see here, if we put our pluses and minuses, this one goes negative, this one positive. Okay, so what's happening at this critical point? Well, here it is again, cube root of 100 decreasing, increasing. We have a minimum. So in fact, we do have a minimum at x equals cube root of 100. Now, we go back, we read the last part of the question. What are the dimensions? This is what we want to report back, the dimensions. Okay, if you remember, and my box was here, but it's erased now, it was x by y. So the dimensions are cube root of 100 meters by cube root of 100 meters by, well, y here It's 100 divided by, maybe I'll write this here, it's 100 divided by 100 to the 2/3, which is properties of exponent. It is also cube root of 100. So this would be by cube root of 100 meters. And this is our final answer. It's the dimensions of this box that will minimize surface area. Before I do any more examples, I would like to talk about another option that you have when you are in this type 2. So this is when we want to maximize or minimize a function that is differentiable, but importantly defined on an open interval. So we are not in the closed interval case where we have the extreme value theorem. Now, this option really comes from the local max and min, and we could have discussed this much earlier in the semester, but I think now is a nice time. So we are still in the case where f has only one critical point, x equals c, but I need a little bit more here. I need the derivative f prime of c to be 0. So this, for example, what I'm about to say, it doesn't apply in the case where the derivative does not exist at that one critical point. But what we will discuss is called the second derivative test, although just like the first derivative test, I don't memorize the statement. And one reason I personally don't mention the second derivative test in the very beginning of the semester is because you can't always use it. I've already mentioned one place that you can't use it, which is when the derivative doesn't exist at the critical point, but there's more. So you will have times when the second derivative test doesn't apply, and if that happens, then your option is to go back and use the first derivative test. In any case, let's discuss this now. So what does the second derivative test say? Well, there are two parts. One is if the second derivative at this critical point is positive, then, and we will make a statement. And then the second part is if the second derivative at this critical point is negative, then, and we will make a statement. And as I mentioned, the statement, if you take off this one critical point part, the statement is about a local max or local min. But in this type 2 situation with just one critical point, we can then conclude we have a global or absolute max or min. And so every time I draw a picture, so we have one critical point, the derivative is 0 at that critical point, and second derivative positive. What does this look like? Well, here's c and something like this, concave up. Right, second derivative positive, concave up, and so the picture looks like this. Well, what do we see here? We see a minimum. So then the statement is x equals c corresponds to a minimum. And similarly here. So now second derivative negative at c, this says concave down. And then also, well, first derivative is 0, so this would look something like this. What do we see here? Well, we see a maximum. So then x equals c corresponds to a maximum. So you see, this is or can be easier than the first derivative test when it works, because you notice I didn't divide the domain into intervals. I didn't have to test a point in each interval for the sign of the derivative to figure out increasing, decreasing. I didn't need any of that. All I needed was to evaluate the second derivative at this critical point. And if we get positive concave up, we have a minimum. If we have negative for the second derivative, concave down, we have a maximum. Now, one more sort of caution, maybe I'll put this at the bottom, and this is why the second derivative test doesn't always work, is if you happen to get that the second derivative at C is 0, or the second derivative at C does not exist, then this test gives you no information. Maybe you have a local max, maybe you have a local min, but you'll never know it with a second derivative test. And what you would have to do is go back and work with the first derivative test. So because of the limitations of this test is one reason I don't stress it at the start of the semester. But now that we have mastered, well, a variety of different topics, if you want to use this to save a little bit of time, it's certainly something you can. So let's do an example where I will use this second derivative test in part of the problem. A rectangular pen has one side against a barn. Let me draw a barn. Okay, and then 200 feet of fencing are used for the other 3 sides. Maybe I will make my fence part purple, like this. And if I call this, let's say X, X, and Y, okay? What is the maximum area of the pen? Wonderful. Well, let's get started with this problem. We want maximum area. So I will write area is, well, it's X times Y. And this is our objective function. And we want to maximize. And then this is subject to a constraint equation. And the constraint equation comes from here, that we have 200 feet of fencing. This would be X plus Y. 2X plus Y is 200. This is the constraint equation. Wonderful. We have set up the problem. Now, use the constraint equation. We will write Y is 200 minus 2X. And then we can write area as a function of X. It's X times 200 minus 2X, which is 200X minus 2X squared. And this would be on, now we need to figure out the domain. Well, X and Y, in order to make a rectangle, X and Y must both be positive. Okay, so X is positive, I can put that. But then Y being positive, if we look at this constraint, it would say that 2X must be less than 200, or X is less than 100. So we are trying to maximize this function on an open interval. We begin by taking the derivative. Look for critical points. The derivative is 200 minus 4x, and when we set this equal to 0, we get x as 50. One critical point. So we are in the beautiful situation where we can use either the first or the second derivative test. Now, I just mentioned the second derivative test, so let's use that here. This involves taking a second derivative. Well, here's the first derivative. Okay, so my second derivative is -4. My second derivative evaluated at the critical point Well, this is a constant function. It's also -4. This says concave down. So I draw a picture, concave down. Okay, what do we see here? Maximum. So this says, in fact, we have a maximum at x equals 50. Okay, using the second derivative here. Now, what's the final thing to do? We want the maximum area of the pen. Well, right here, maybe I will underline it in pink. This is area as a function of x. And so all I need to do is just evaluate this at 50. The final answer is a of 50, which is 200 times 50, like this, minus, we have 2,500 times 2, and that gives me 5,000. Then we subtract. So this underlined is the maximum area, 5,000, and this is in feet squared. Okay? So this is our final answer here. Now for my last example, a rectangle is inscribed in a circle of radius 3. What is the maximum area? Here is a picture, and this green circle is supposed to have radius 3, and I just drew a rectangle inside. Well, let's start labeling things. If I call this length x and this length y, now here's the center, and so this length here is 3, and then similarly this length here is 3 because they're both equal to the radius, and this is a right triangle. So what we see here, if we use the Pythagorean theorem, that x squared plus y squared is 6 squared. And this is our constraint equation. And we want to maximize the area of the rectangle. Maybe I should add that for clarity. The area is x times y, and we want to maximize. So here is the setup. Well, here y squared is 36 minus x squared. Y and x are both lengths, so they are both positive, which means y is the positive square root of 36 minus x squared. Now I can write area as a function of x. It's x times the square root 36 minus x squared. And this is on, well, x must be positive, and x must also be less than 6, which is the diameter of this circle. So we want to maximize this function on an open interval. Okay, we must look for critical points. Now this is the most intricate function we've had to differentiate today, but we certainly have studied how to differentiate things like this. The first thing I see is a product. Those first times the derivative of the second, which is a chain rule. This is derivative of the outside evaluated at the inside, and then times derivative of the inside function. So first derivative of the second plus second times derivative of the first. But the derivative of the first is 1. I
I need critical points. I need to set this to 0, and this is one of the times where you do want to simplify because, well, I have to set this equal to 0. So first I will write it, well, minus 2 times a half is negative 1, and in the numerator I have an x squared. In the denominator I have a square root, 36 minus x squared. And then I will add, so let's get a common denominator, which is square root 36 minus x squared, and this term, the numerator, will be 36 minus x squared. One more step, maybe I'll do it here. This is 36 minus 2x squared, all over the square root 36 minus x squared. And this is my derivative. Okay? Simplify. Now, to set this equal to 0, fraction is 0 only when the numerator is. I can set the numerator to 0. I get 2x squared equals 36. X squared will be 18. We get x is square root of 18, which you can certainly write as, let's see, 3 times square root of 2, but I'll just leave it like this. Now, I'm about to erase and just write on the board some things that I need to move forward, but let me just say, there's always the question of, what about the derivative not existing? Especially here, we have something in the denominator, but the only time the derivative does not exist is outside of this open interval. So I do in fact have only one critical point in the open interval, and that is x is the square root of 18. On the board, we have area as a function of x. I rewrote the derivative, simplified that we calculated, and we found this square root of 18 is the only critical point on this open interval. Now I need to check, because I'm trying to maximize this area, I need to check that square root of 18 does correspond to a maximum. And because it's the only critical point, I can use first derivative test or second derivative test. Now, here, looking at this first derivative, in order to do a second derivative test, the first step is calculate the second derivative. And here it would be a quotient rule together with a chain rule. When I go to differentiate the denominator, then I have to evaluate and simplify enough to see if the second derivative is positive or negative here. So I'll just say, for me personally, I think a first derivative test is easier just because I don't have to go through differentiating a second time. So let's do that here. We will draw a number line, and the intervals here would be open 0 to square root 18 and square root 18 to 6. And then we pick something in each interval. Okay, let's use x equals 1, x equals 5. This is bigger than square root of 18, well, namely because 5 squared, 25, is bigger than 18. Okay, so a prime at 1, this is 36 minus 2, this is 34, divided by something that's positive, right? The denominator is always positive. So this is positive. A prime of 5, well, let me actually write what it is. A prime of 5 is 36 minus 50 divided by the square root of, I'll just write it, 36 minus 25. This is negative. Okay, so if we write it under here, it goes plus, minus, and you see the function increasing, decreasing. In fact, we do have a maximum at x equals the square root of 18. And the final step I will put down here is, what do we want? We want the area, which is a of square root of 18. This is the square root of 18 times, the square root of 18, which is 18. Okay, so this is the maximum area here, 18.